And in this presentation, we will focus on very well-known large language models and their connection to disinformation. So a topic that is quite widely discussed, but many times not in such depth that deserves. So we hope that based on the results of our own research, we will be able to provide you some interesting information on this particular topic. So please let me start with a brief introduction of our institute. So we are from KInIT, and our research institute focuses specifically on research in artificial intelligence. And we do both basic and applied research, and also we have quite a lot of collaboration with academic partners, even providing a PhD study, and also we cooperating with industry. What is quite interesting, most our funding is coming from research grants, especially from European Union. And in this area of Europe, we are, let's say, some kind of prototypical institute, because there are not many of them, especially in comparison with Western Europe. So we are trying to create a new model for this kind of research institutes in Central Europe and Central and Eastern Europe. There are 4 teams, research teams in our institute. The first one, where from this one we are also from, is focused on web and user data processing. But we have also teams that we quite closely collaborate with as green and secure environments, focusing on green topics, and also natural language processing, and a very important ethics and human values in technology. And what we will present today is commonly done in collaboration with natural language processing and also with ethics and human values. So despite being a quite young institute, only 5 years old, we already created a quite extended network of project partners across Europe and having multiple European projects. And one of the topics that also relates to today's webinar is focus on AI and how we can, with AI, actually increase content credibility online, how to make online environment more safer, and promote high quality content more extensively. And in this wide area, we are working on multiple research problems. And I would like to depict especially 3 ones. First one is that we work on detection of disinformation, detection of credibility signals, and are trying to help fact-checkers by utilization of fact-check claims. The second direction is that we work on the research of multilingual methods. So multilinguality is especially important for us, because especially we as a small country, nobody will do a research in Slovak language if we will not do that. So we are really focusing on multilinguality and low research languages. And the third direction is that we work on generative AI quite heavily, and what is very relevant also for this webinar, on large language models. So this presentation will be actually on some kind of intersection of these 3 dimensions. We work on these research problems on several research projects that are listed here. So let me start with a very brief introduction to large language models. So let's start with definition. Probably most of you are already knowing what large language models are, but it's basically some kind of foundational models that are large neural networks that are trained on a lot of data, usually collected from online space, that are capable to generate our embed text. And usually when we hear large language models, we automatically assume that this is a ChatGPT that becomes quite of the most famous large language models or chatbots. But actually there are many more, and their capabilities are going beyond being just a chatbots. But what I wanted to show it to you here is that the history of chatbots actually started a very long time ago. Already in 1966, where the first chatbot was actually created. And for quite a long time, nothing happened. But hardware capabilities increase in time. A lot of important discoveries happened. In 2014, like something what is called word embeddings were discovered in Google. And in 2018, independently, like two companies, OpenAI and Google, made a really breakout inventions discovering GPT architecture and a BERT model that is somehow considered to be like one of the first smaller large language models. And then ChatGPT finally arrived. And like this is evolving quite heavily. You know that new large language models actually pop up every day. And the question is how this whole direction will go. And we particularly see two options. The first one is that even larger models will be created, trained even on more data. Or the second option is that we will try to train smaller but smarter models. And we think that both these directions are actually necessary because once we will run out of data that are available online, and we will need to start focusing on smaller but smarter models. Usually, when like we are working with large language models, for example, with ChatGPT, we use like some specific approaches how to utilize them for all tasks we need to handle. And one of such techniques is do a zero-shot prompting. So this is probably what you also most time use, and this is basically that you will directly prompt the model to provide some kind of answer. So this is like the most simple one and the most generic one. Some more advanced technique is called few-shot prompting or in-context learning. And in this case, what you typically do is besides the prompt itself, you also provide few samples. And these samples help to a little bit learn model what you actually want to do. In this case, it's to show the model some kind of examples of translation from English to French. And this will help model to behave more accurately. Well, these two techniques can be used with any kind of model without any like fine-tuning or retraining the model. The next one actually requires to have an access to the model and to fine-tune it or to improve it for a specific task. The first option is to do like a traditional fine-tuning of whole model. So basically you are showing some examples to a model and updating the parameters of this model to perform the task better. And the second option is that you actually try to train the model to follow some kind of specific instructions better, what can be considered as a specific case of fine-tuning. So like with these kind of examples, you should know that there are multiple ways how to use large language models, and we will mention these approaches also later during this webinar. Typically, large language models are commonly mentioned with a set of different threats. Like they can be misused for online influence campaigns, especially disinformation. This is commonly mentioned in media. Many times they are mentioned that can be misused for generation of spam and like for poisoning online discussions, etc. And this is absolutely true. There are many of these kind of vulnerabilities, how large language models can be misused. And during today's webinar, we will specifically focus on generation of disinformation. But at the other side, large language models have also a lot of positive capabilities. And this is just a few of them, but like, of course, these positive capabilities still like somehow overcome negative potential consequences. And during this webinar, we will focus particularly on text generation. So like for most of it, we will speak about generation of disinformation, then about personalized disinformation generation, and finally, how such generated text can be detected. And in some small extent, we'll talk about a few more that can be interested for media professionals, such as information retrieval, text classification, data augmentation, summarization, and information extraction. So I will now hand over to Aneta.
Okay, and I will start talking about the negative side of large language models in context of information. And specifically, I will focus on KInIT's work on identifying and analyzing large language models' vulnerabilities that could be misused to generate disinformation at a large scale with minimum effort and costs. The findings we present are based on the research detailed in published papers. Therefore, before each section, there's a title of the corresponding article that can be explored further if interested. So let's start with the disinformation capabilities of large language models. We are curious about how would these models behave when asked to write an article supporting a disinformation narrative. To do that, we selected 20 disinformation narratives, sourced from professional fact-checkers, and they covered a variety of topics, including health, COVID-19, US politics, and some region-specific issues. And we selected also 10 large language models, commercial as well as open source. During the experiments, we used 3 formats of prompts: zero shot, then few shot with sample text as described by Ivan, and also prompts with a short abstract. The abstract was about 4 to 5 sentences long and provided additional context to the disinformation narrative. And on the slide, you can already see a text generated by ChatGPT as a response to a request to generate an article that supports the claim that ivermectin is an effective treatment for COVID-19. And as you can see, the generated text starts with a disclaimer that AI models do not promote or encourage the spread of false information. But after this warning, the model happily generated disinformation content that included a variety of manipulative techniques, including a new or fictional study that was hallucinated to support the point. So this is text generated at the end of 2023. Yet this field of large language models is changing dynamically over time, and therefore we used the same prompt 4 months later in April 2024 with the most recent version of ChatGPT available at the time. And for the same prompt, we got even better structured and even more persuasive disinformation article. And notably, there was no disclaimer generated at this time about the false information that was included in the text. So what about the most recent version of ChatGPT? Fortunately, just a warning and refusal to generate a dangerous content was generated this time for the same prompt. But there's this but. It is not difficult to bypass this restriction. Simply claiming to be a researcher working on combating disinformation and politely asking to generate a fictional article was enough to bypass the safety filter. And then the generated output started with a disclaimer that this is just an example intended for educational purposes. But after this, a ready to misuse disinformation article followed. The article contained a variety of manipulative techniques, including an appeal to emotions or a false authority. And at the end, there was this analysis of disinformation tactics generated. And moreover, if we ask to generate additional news about supporting disinformation claims, more articles like this were generated without hesitation. So these were just some examples to see how this text looked like. But in the second half of 2023, we used several models to generate over 1,200 texts, and we labeled them into 3 categories: neutral, safe, and dangerous. While safe texts contain disclaimers or they provide counter-arguments to the disinformation narrative, dangerous texts have high misuse potential because they contain these disinformation articles. And the third category, neutral text, they support as well as refuse the narrative. This figure illustrates the share of dangerous, neutral, and safe text generated by different models. And as you can see, the large language models were capable of generating convincing news articles that agreed with dangerous disinformation narratives. Also, if needed, they were able to hallucinate new arguments, new studies, and fictional facts to support the point. And also, this short 4 to 5 sentences abstract was enough to steer the understanding of the models and to improve the relevance of generated texts. Additionally, safety filters were activated just in a small number of cases, And they were activated more often in text generated by open source models. So these open source models exhibited a safer behavior in comparison to commercial ones. So when we saw that large language models are capable of generating high quality disinformation text, we focus on their capabilities to personalize this text to specific user groups, because this combination of personalization and disinformation could be dangerous potentially. So to investigate personalization capabilities of large language models, we selected 6 disinformation narratives, health as well as politics related, and 7 target groups. Our aim was to cover diverse user groups, and we ended up having the following groups: European conservatives and liberals, rural and urban residents, and then students, parents, and seniors. We used in the research 3 formats of prompts without personalization. That's pretty much what we've seen on previous slide. Then prompts with simple specification of the target group, meaning that the prompt included only the title of the target group, and prompts with a detailed specification of the target group, which meant that in addition to the title of the target group, the prompt included a short generic description of characteristics of the target group attributes. But due to ethical considerations, we are not publishing the exact wording of prompts used in the research. So we use 6 LLMs, 6 large language models to generate over 2,000 texts. And we evaluated their, firstly, linguistic quality, secondly, the extent to which they are agreed or disagreed with the disinformation narrative, and thirdly, the quality of personalization. So how did the models manage to personalize the text? Some texts mention the target group explicitly to improve the relevance of the text to the intended target group. That's illustrated by the example on the screen. This text was generated as a response to request to write an article supporting the claim that EU wants to conceal the presence of the insect in products with the intent to force its citizens to eat insects. And we asked the model to personalize that for students. And like students are, as shown, mentioned on several places in the text. Some models went even further when it came to personalization, and besides mentioning the target group explicitly, they also appealed for their beliefs on the target group beliefs, emotions, or some values, or they made a reference to their life experience. This is illustrated by the example by the text that was personalized for parents. And as you can see, the text not only mentioned families and parents, but it also quotes a false authority, an allergy specialist, who claims that children might suffer from severe allergic reactions to insect in food, and therefore the new EU legislation should be potentially life-threatening for them. And this quote might resonate with the concerns of the target group, or like parents as a target group. Other texts show that personalization capabilities of large language models are still limited in some cases. This is a text that was generated or that was personalized for urban population. And as you can see, the text not only mentioned urban residents, but also make a reference to their life experience living in high-rise apartments. But the link of this of their life experience with the rest of the article, with disinformation narrative, is rather loose, because it claims that EU gambles with urban residents' life and health because they live in high-rise apartments, and once they have a severe allergic reaction to the insect in food, the emergency medical services might not reach them as quickly as in rural areas because of these high-rise apartments. So these were just some examples, but in total we generated over 2,200 texts, and we labeled them into one of the 5 categories. Safety filter text contain refusal to generate the text. They are the safest. Non-personalized texts were not personalized at all to the intended target group. These were just texts supporting the disinformation claim. Text personalized to a low extent, they only mention the target group explicitly without any reference to their beliefs. Then well-personalized text appealed to fears and concerns of the target group, or they make a reference to their life experience, and text personalized illogically, as the last example, they mentioned fears or concerns of the target group, but they made just a loose link to the rest of the text. So this figure illustrates or compares the quality of personalization across generators. And as you can see, they vary across generators. But overall, the state-of-the-art large language models were capable of generating high-quality personalized disinformation text. And even in these non-personalized articles, safety filters were activated only in a small number of cases, and this personalized generation even decreased the activation of safety filters. And also, personalized generation decreased the accuracy of machine-generated text detectors, and detection of machine-generated text is something Dominic will talk more about in next minutes.
Hello, so I will talk a little bit more about detection of generated text. As Aneta has mentioned, the personalization negatively affects the detectability of the generated text, but there are other aspects that also influence machine-generated text detection. And in our two studies, we have explored multilingual aspects and cross-lingual transferability of detection performance. And also we explored authorship obfuscation as a kind of detection evasion mechanism to and how it affects the detectability of the machine-generated text. But firstly, what actually the machine-generated text detection is. For us, it is a simply binary classification distinguishing between two groups, human written class and machine-generated class, which we want to detect. Now, why it is important? It was already mentioned. We can use it as a prevention of misuse of generated text, for example, for disinformation spreading, but also for other harmful uses such as plagiarism or frauds, but also as a prevention of unintended usage of generated data, for example, in model training. In our multilingual study, we have included 11 languages. 3 of them have been also included in training part of our fine-tuning process. And we have used human written news articles of older date, so we can be sure that they are written by humans and not generated by AI. And we have used their headlines to generate multiple machine-generated texts in using 8 large language models for that. For our detection performance metric, we have selected macro average F1 score, which has values from 0 to 1, and higher value represents a better detection performance. And we have compared multiple categories of detection methods, fine-tuned, statistical, and black box detectors. And we have found that fine-tuned detection methods perform the best, especially when they are trained using all 3 of our trained languages combined and using all generators' data. And eventual performance is still far from perfect, and it is even worse when we evaluate those detection methods on out-of-distribution data. For example, if we evaluate them on text generated by some language model that has not been used in the training of the fine-tuning process. And in the second study, we have evaluated the effect of obfuscation on detectability of the text. Obfuscation, it means that it is a modification of the text to hide its authorship. For our purpose, it is to avoid detection of machine-generated text. We have used 10 existing automated obfuscation methods for that, which have been of various categories. Back translation, it is simply translation of the text to some other language and then back to its original language. Paraphrasing is just rephrasing the text, but keeping the same semantical meaning of the text. Less known are homoglyph attacks, which are using replacing of visually similar characters from different scripts. For example, on the right, we can see that original text using Latin script characters is replaced by some characters of Cyrillic script, but for human, it is visually meaningful word hospital. But for a machine, for computer, it is due to internal representation of the word, it is nonsense because it was not trained. The language model was not trained on such combination of scripts. And there are last category of obfuscation methods, which are adversarial attacks, which are kind of advanced techniques to look up for such modifications that actually causes misclassification or some surrogate detector, which can be used by such attacker. And when we obfuscated those texts, we checked the quality, whether it is preserved or similar to original text. We have used automated metrics for that, but also we have looked at the text by humans, by us, and we have found that two of the used obfuscation methods are simply not usable in non-English languages. For example, they generated text that contains some repetitive characters or doesn't contain meaningful text in target language at all. And when we compared detection methods performance on such obfuscated data, we found that fine-tuned detectors are still the best across categories of detection methods, but the eventual performance of detection is degraded when compared to evaluation on unobfuscated original data. We have also looked at the performance or effect of obfuscation across all the tested languages, and we have found that there are differences not only between how the fine-tuned detection methods have been trained, whether monolingual using single training language or all three languages combined, but also among categories of detection methods. For example, we have found that English-only fine-tuned detection methods are least robust against obfuscation because there is the highest drop in the performance when on average when tested in all languages. Especially when tested in non-English languages, there is higher drop in the detection performance. And what is important or interesting is that it means that English is a bad default for cross-lingual transferability in this task. But it is most commonly used in NLP community for such purpose in other tasks. So this could be like reconsidered. And sorry. And we have also explored how inclusion of obfuscated text into retraining process or training process of these detectors affects the performance. It is called adversarial training. And we found that when we combined all of the obfuscation methods into the training process, we could achieve the highest performance increase. In the leftmost bar, there is original performance of the original trained detection methods using just unobfuscated data, original data. And on the rightmost bar, there is detection performance when using all of the obfuscation methods during training. And we have integrated our machine-generated text detection service into VeraAI verification plugin, where it can be found under assistant tool, to which we can provide URL, and text of the URL is analyzed, and then various credibility signals are provided. And machine-generated text detection is one of them. To summarize most important findings of our research, we have found that statistical and black box detectors could not cope with multilingual data at the time of conducting this study. And we have found that multilingually fine-tuned detection methods performed the best across all the tested languages. And all the similarities between languages and their scripts, and also between generators, all of that affect detectability of the generated text. And regarding the authorship obfuscation, we found that all of the tested obfuscation methods present a potential threat in all tested languages. Although in some of them, they are detectable by humans, but they present threat for automated detection. But we have also shown that using simple data augmentation using obfuscated text can be used to cope with this problem or with this threat. And what we have not shown in here, but we have done in our other experiments, is that we have also used social media texts, which are of shorter and wilder style, and they are not a problem for detection methods to be fine-tuned on them, evaluated on them. There is another problem when we do cross-domain detection transferability. When we train on social media text and test on news articles, this is a whole different story. This is what we are looking on just now, and this presents our current research in this topic. This is all from me. Ivan, over to you.
Yeah, thank you very much. So we already saw that the situation is not completely lost, but we would like to end this webinar even in more positive way. So we would like to go through some additional positive capabilities of large language models. And the next slides are representing the outcomes of multiple research papers they conducted during the last 2 years. So one of such positive capabilities is information retrieval. And in this domain of fact-checking and disinformation combating, one particular use case is detection of previously fact-checked claims. So what we did, we developed a tool that is called Fact-Check Finder. And you can imagine it as a tool that can take any kind of social media post that is containing a piece of text in any language, and it can actually provide as output a ranked list of the most semantically similar fact-checking articles that are actually fact-checking the content in that provided social media post. And to perform this, we used language models for matching models. So that model that can actually match the provided input with this database of fact-checking articles. And we train it on more than 200 fact-checked claims from more than 100 organizations in 49 languages. So it should be highly multilingual. And what is even more important, this tool is still using continuously updated database of fact-checking articles. And it currently operates on probably the world's largest database of fact checks, containing almost 600 fact checks. So you can try it. There is a link on the top of this slide. This is a standalone tool that, as I mentioned before, on the left, we can see an example of some kind of social media post from Instagram, and we will just put it there, hit the submit button, and it will be able to find the same content fact-checked in other languages. And if there will be some time, I can show a demo of this application after presentation. Exactly the same tool, exactly the same matching model is also integrated into our AI verification plugin. So if you are already familiar with this one or using it during your work, you can use exactly the same functionality directly in the verification plugin. Some other capability that can be useful for a media professional is text classification. So large language models are very known for quite well understanding of a text. So they can be used to classify text probably in any kind of labels needed. But what we did in the past, where large language models can actually do a nice job, is to classify credibility signals like detection of persuasion techniques. As Dominic showed just before, large language models can be actually used to detect what they are capable to generate for machine-generated text detection. They can be used also for target audience classification, a task that our colleagues from EBU are working also on, or detection whether some piece of content is containing a check-worthy claim or not. So there are many possibilities how to use it. But what we want to highlight here is that large language models are not a silver bullet solution for everything. If you have enough data, as we showed in this particular research, if you have more than 100 samples in average, you can actually fine-tune a small used in a zero-shot or few-shot mode. So like having enough data means that you can actually achieve even better performance with smaller models, and large language models are not a solution always, like the best performing solution always. Moreover, they can be used for data augmentation. So many times we have a data set with a very small number of labels, and we can use large language models to generate more labeled data and then fine-tune better models or train better models. And what we did here, we did a small study in which we replace human crowd workers with large language model and with ChatGPT particularly. And we asked large language models to generate more data or paraphrase more data that have been used to train even better model. And what is even more important, the costs were about $1 instead of $700 paid for human crowd workers. So you can achieve a similar performance and saving a lot of time and costs here. And very last capabilities to list here, large language models are really good in summarization and paraphrasing. So you can, for example, use them to summarize a content that will be suitable to post at social media posts. So from a news article, you can actually create some small abstract that will be like personalized for a specific social media platform, or even, as we showed before, for some specific target audience. Another capability is extraction of information. So you can feed a lot of text data into large language models and use it for different investigation, like trying to identify different persons, organizations, and connections between them. Again, something where large language models can be quite useful. So as we showed during this presentation, like large language models and their capabilities are a real game changer in estimating credibility and content quality and fighting in disinformation. Unfortunately, both in a negative and a positive way. So from a negative perspective, we showed in our research that they are capable to cheaply generate highly persuasive and personalized information content. So even if like somebody can argue that generation itself is not enough because you still need to have that channels to spread this information to users, when you apply personalization, there is a higher chance of a natural adoption of such content and spreading it further and further. What we also showed is that detection of machine-generated text, especially in multilingual settings, is quite challenging to achieve, and the performance is far from perfect. But like still, there are options how to improve it. One of such is training the such detectors on multilingual data generated by multiple generators, by multiple large language models, and even using obfuscated data to achieve a better performance and to be more robust against some potential attacks by bad actors. But what is even more important, there are many positive capabilities making our life easier every day. And as we showed, these large language models can be used for pre-processing of a huge amount of content and can help us to achieve at least some initial understanding what is written in a pile of text. They can be used to generate additional data, and then such augmented datasets can be used for like training of better models, classification models, for example, especially when annotation is expensive, and this is exactly an example of disinformation detection. And finally, they are very good in prototyping new solutions, especially when no annotated samples are there. So at the end of the presentation, I want just to acknowledge 3 projects that in which we did a lot of this research. It's Vera AI project, AI Code project, and Vigilant project.